start with the basis of what an atom is, how it really came about, right? Or not really how it came about, but how we learned about it, how we discovered it, and then the theory that we kind of commit to currently into what we believe about the atom, okay? So we're going to start all the way back, okay? We start all the way back with someone named Democritus, okay? Have you heard that name before? He's a scientist, philosopher, he's a super old guy, right? Okay? His theory was that all matter can be broken down. Any type of matter, we can break it down into smaller and smaller and smaller pieces, right? That's what he said. Any type of matter can be broken down into smaller pieces. When we say matter, that means anything that has mass and takes up space, okay? So anything that has mass and takes up space, he said we can break it down. He said we can break it down until we reach a most basic unit. And beyond that point, he said it was indivisible. What do you think that basic unit is? The atom, right? He called it the atom. Okay? We called it the atom because it means indivisible. Okay, so he said once you break down this matter to the most basic unit, then it can't be broken down any further. This theory was controversial at the time, right? Controversial at the time because it came after Aristotle. Okay, so really, essentially, no one believed him. No one really bought into this theory of the atom or of the fact that you could break things down because Aristotle came before him. Okay, and Aristotle had a completely different theory on what matter was made of. Okay, we're not going to dive a whole lot into the intricacies of his theories, but Democritus was kind of the first one to really go into the atom, okay? But at this point, no one really believed him, okay? Because Aristotle came first, and Aristotle said matter was whole. It was a whole thing. That was it. You can't break it into smaller pieces, right? He went really as far as to say there's only 5 types of matter, and you can dive a little bit more into his theories with that. But he said everything's a combination of these 5 things. And today we know, that's not true, right? Look how many elements we have on the periodic table.
Keckner to the office, please.
Okay, and so Aristotle says we've got these types of matters. It's just a combination of those things, and that's it. And we don't break it down, okay? People followed his ideas for 2,000 years, right? People really bought into this idea because what Aristotle explained was very, and the way he explained things was very, intuitive. Right? It seemed well, that makes sense. So that has to be true. Right? And it didn't really lead people to feel like they needed to dive in further. Right? His ideas were very comfortable. The same thing was true with what he taught about gravity, with what he taught about all these different scientific theories. He taught what seemed to be acceptable at the time, and everyone just rolled with it. Right? Because he was a smart guy and knew a lot of other stuff. But he was wrong on this one. Okay? So we're going to skip way forward now. Into the 1700s, there was people that we'd already discovered at this point, we really had it kind of nailed down what an element was. An element has individual characteristics. Elements have a certain makeup and a certain configuration, right, that makes them different from other elements. Okay? By this time, we're probably only at about 40 to 50 elements discovered at this point. By the time we get to the 1800s, we're at about 60, and then it really kind of blows up from there. But if we start thinking about the elements and what they know at this time, it's not a lot, right? They know that elements are different from one another, and that elements make up all the other things. That's about all they know, okay? They had an idea about what chemical reactions were, but they're not really sure what makes a chemical reaction. They're not really sure what types of chemical reactions we have. And so all of that stuff has to kind of be developed, okay? But what they do know led them to I don't want to say discover, it led them to conclude a couple different scientific laws, Okay, and so we're going to talk about 3 laws here. The first of which is called the law of conservation of mass. Have you heard that one before? Law of conservation of mass. What's the tagline for the law of conservation of mass? Mass is neither created or destroyed. Good, right? You can usually start it with that and finish it. So mass is not created or destroyed during ordinary chemical reactions. All that it does is it changes form. Okay, so mass is not created and it is not destroyed. I would maybe underline that one, highlight that one, so that you know this law of conservation of mass is really, really important. And it's kind of the basis of what chemical reactions are founded on. Okay, another way that for us to think about the law of conservation of mass is to basically say whatever gets put into a chemical reaction has to come out of that chemical reaction. Okay, it might be in a different arrangement, it might be in a different form, but whatever goes in has to come out. So if in my chemical reaction I put in 4 hydrogen atoms, those same 4 hydrogen atoms have to come out. They might be paired 2 and 2, they might be bonded with different things, but whatever goes in has to come out. It's not going to disappear to nowhere, and it's not going to appear from nowhere, right? That's all the law of conservation of mass says. So it's intuitive, but it took a little bit to get there, okay? The rest of their kind of experiments about chemical reactions led to something called the law of definite proportions. The law of definite proportions. Okay, like I said, we're going to talk about 3 scientific laws that came up here, but the law of definite proportions says a chemical compound contains the same elements in the same proportions regardless of the size of the sample or the source of the compound. So that's a lot of words to basically say once a chemical compound is established, it keeps its formula, right? That's pretty much it. Okay. I'll give you a second to get that written down and then I'll talk through a little bit more. All right, so if I look at the law of definite proportions and I look at water, for example, water has a chemical formula of H2O. Okay, that means for every molecule of water I have, it has 2 hydrogen atoms and 1 oxygen atom. Okay, every sample of water, of pure water that I pull would have the relationship of 2 hydrogen atoms to 1 hydrogen atom. Right? Does that make sense? The proportion is the same. Okay, so that means if I look at its mass in this compound, 11% of the mass is made up of hydrogen and 89% of its mass is made up of oxygen. So that means no matter what size of sample of water I pull, I know that that sample is 11% hydrogen and 89% oxygen, right? I just know that based on the chemical formula for water, right? And if I said, oh, this is water also, H2O2, would that be true? No, it wouldn't. Right? The proportion is not the same. It has a different chemical formula. This would behave much differently. It has lots of different properties. This is actually hydrogen peroxide. So not something I want to drink. Not something my body is made up of. Right? Very different for having just 1 oxygen different. Okay, so it behaves very differently. So law of definite proportions just says once a compound is established, then it behaves a certain way and it has that same proportion, no matter what. Okay? All right. Once we get to this point, we've got a little bit more understanding about how chemical reactions work, how compounds are formed, right? But we also knew that we can combine 2 elements in a lot of different ways to form a lot of different compounds, right? As long as they are in different proportions. So if I look at carbon and oxygen, for example, carbon and oxygen can form CO2 and it can form CO. Do you know what those formulas are? CO2, what is it? What do we call it? Carbon dioxide, and what's CO? Carbon monoxide. Carbon monoxide and carbon dioxide. Are those familiar terms? Right? Are they good for us? They are not, okay? Neither of them are really good for carbon monoxide is very bad. Carbon dioxide is not good in big proportions, right? But they mean two different things, right? They behave differently. And so this is called the law of multiple proportions. And all that this says is that we can form chemical compounds by combining atoms in different ratios. Right, so we can form lots of different compounds by combining these elements in different ways. That's really all that it's saying. Okay. Okay, this is especially true when we start dealing with carbon and hydrogen. Okay, called hydrocarbons. They combine in lots and lots and lots of different ways. But we can see chemical compounds form from lots of different proportions. Why do you think it says it's by whole atoms chemically combining? If I know that water is H2O, can I also have a formula that's H1/2O? It's the same proportion, right? But can I have half of a hydrogen atom? No, I can't. Right? That's an important thing about atoms, okay? Let me just think about this here. If I'm looking at CO2, okay, and I want to take that and do something crazy and make it C1/2 and O, right? It's the same proportion, but that doesn't work because half of a carbon atom is no longer a carbon atom, right? The thing that makes a carbon atom is that it has 6 protons. But if I cut that in half and now only have 3 protons, it's not carbon anymore, it's lithium, right? So it's not just about a half of an atom. That's not possible. When I change the number of protons in an atom, I now have a different type of atom, okay? So the thing that makes elements and atoms unique is the number of protons they have. And if I try to cut that in half, then it's no longer that type of atom anymore, right? It's a new type. So we can't do that. It's got to be whole number ratios. All right, now let's talk about what we know currently about the atom. Okay, this is modern atomic theory. So this is what we think currently about the atom and what we know currently about the atom. We know that all matter is composed of atoms. Okay, atoms make up all matter. Okay, all matter is composed of atoms. Some of the parts of the atomic theory seem very obvious, right? So feel free to ad-lib when you write it down. Don't feel like you have to write down it word for word, because some of them I feel like are very intuitive. Okay, like this one. Atoms of one element differ in properties of another element. Okay, all that's saying is that we have all that's saying is that oxygen atoms behave differently than hydrogen atoms, and hydrogen atoms behave differently than carbon atoms, and differently than phosphorus atoms, and whatever. But atoms of different elements behave differently. They have different properties. Okay? So these are the two main parts of this atomic theory that I want you to know. There are a couple other points in our modern atomic theory that we're not going to touch on today. But there are other parts that we'll start to talk about as we start looking a little closer into protons, neutrons, and electrons. So we'll add to this atomic theory kind of as we go through. Okay, but those are the main 2 parts for right now. I do want you to have down the definition of an atom, what we know today's definition of an atom is, and then I want to hit kind of the high points after you get that definition written down. So here is the definition of the atom. I would like for you to have that written down, and then I want to highlight a couple parts of that. All right, a couple parts of this definition that I want you to kind of highlight. It says the smallest particle of an element that retains the chemical properties of that element. It retains the chemical properties of the element. What do we know that what do we know that is inside atoms? What 3 things? Protons, neutrons, and electrons. So technically, the atom is not the smallest thing, right? Electrons are the smallest thing. But electrons don't behave like oxygen. Electrons don't behave like hydrogen, right? In order to behave like hydrogen, it has to have a certain arrangement of protons, neutrons, and electrons to be considered hydrogen, right? Just like we individually have to have certain characteristics that make us us. We're not just bones and whatever, right? We have a certain characteristics that make us ourselves. And elements are the same way. We can't just talk about the parts that make it up, right? It's got to have a certain configuration in order to be oxygen or to be hydrogen or carbon or whatever it is. So the atom is not just the smallest part of an element, because if we're talking about the smallest part of an element, it would be an electron. But it's the smallest part of an element that maintains the chemical properties of that element. So it's got to have the right configuration of protons, neutrons, and electrons to be considered an atom. Okay, so that's really important. All right, now we're going to walk through what's inside the atom, right? We kind of know what parts are inside the atom, but now we're going to figure out how did those things get discovered, how did it come about, all that kind of stuff. So we're going to start with the electron, right? Discovery of the electron. I don't know why it says continued. I rearrange these slides all the time. So discovery of the electron. The guy who discovered the electron goes by the name of J.J. Thompson. J.J. Thompson, he did an experiment, and we're not going to dive into his experiment too much, but he found out that basically metals always give off a negative charge, right? They have this negative charge about them. We've got this electricity or this negative charge thing moving through these metals. He went on to discover that no matter what type of metal he was working with, they all gave off this electric, right? And then he kind of concluded that, well, if it happens in metals, it's got to happen in all of them. Okay, so he called this negative charge and these particles, he called them electrons, right? His experiment, I'm dumbing it way, way down, right? It's obviously an intense thing that required a lot more work, but he called these particles electrons. And he was able to conclude that if all the metals I tested, if all these different scenarios have electrons, then I think they have to be in everything, right? They have to be in every element. If they're in all these metals I tested, I think they're going to be in everything, okay? So he was the one that really discovered the electrons. Later on, not by him, but it was discovered that the mass of an electron is really, really, really teeny tiny. You're not going to have to know this mass off the top of your head, but it does give us a context as to how small it is, right? An electron weighs 10 to the negative 31st kilograms. So that's pretty small, right? You've got 30 zeros happening in front of those numbers. So it's a teeny, teeny, tiny amount of mass. A proton weighs about 2,000 times that of an electron. Okay, so a proton has a mass that's about 2,000 times greater than an electron's mass. So for all of our intents and purposes, electron mass is negligible, right? We ignore the mass of electrons. If it's 2,000 times lighter than the other parts of your atom, really no need for us to use that, right? So he knew they were there, knew they didn't take up much mass. Other things we gathered from his experiments is that if atoms are neutral, there's got to be some positive charge that's offsetting these electrons, right? Let's think through that for a second. If he knew there's an electric negative charge, but he knew all atoms were neutral, there's got to be something that's offsetting that. Agreed? Right? What offsets a negative? A positive. And so he called these protons. Okay? He called them protons. I don't know that he gave them the name. I shouldn't have said he, but they were called protons. Okay? And he also then concluded, if I know electrons are so teeny tiny, there's got to be something else that's contributing to the mass of my atom, but not the charge. So what particle is it that contributes to mass, but not charge?
Neutron.
The neutron, right? So these are some things that we learned from his experiments, right? We gathered these kind of general ideas. Once he discovered electrons, we then had to say, well, there's got to be something that's offsetting that negative charge. We'll call them protons. And then there's got to be something that's helping contribute to the mass of an atom, because we know it's not electrons. And so we called those neutrons. So here's Thomson's model of the atom. Okay, it's called the Thompson Model. Sometimes it's called the plum pudding model. I don't really know why. Okay, plum pudding. I've never eaten plum pudding. I don't really know what it looks like. I assume it has chunks floating in it like this or something. Okay, but the Thompson model just says we've got an atom, and within that atom, the negative electrons are just dispersed evenly throughout the atom, right? That's all that the Thompson model shows us, is that we've got this spherical atom, and that within the atom, the electrons are very evenly dispersed. Okay, that theory is going to be busted in just a little bit, but this is the first real atomic model we kind of start to take seriously. Okay, because it does show what we think is happening. Okay, so there's the Thompson model, otherwise maybe called the plum pudding model, but it's just got an even distributions of electrons throughout throughout the atom. Okay, into a new type of atomic theory or atomic model, and this is when we discover the nucleus. Tell me what you know about the nucleus already.
It's the center of the cell.
The center of the cell, good. But we're thinking about the atom, so even smaller than that. Do we know what's in the nucleus? Protons and neutrons. Protons and neutrons. So let's figure out how we got there, okay? So this guy is really important. This one you'll have to know the name of, okay? This guy's name is Ernest Rutherford, and he's responsible for the discovery of the nucleus. He ran a really, really famous experiment called the gold foil experiment. Have you heard about that before?
Isn't it like the golden boat?
No, it's called the gold foil experiment. Maybe write that down with his name. Okay? Rutherford ran something called the gold foil experiment. It's a super, super famous experiment. Okay? And what he did was he shot this gold foil with something called alpha particles. Okay, something called alpha particles. And the only really thing you need to know about alpha particles is that they are positively charged. That's a really important part of this. Alpha particles are positively charged. Okay, they happen to be heavier than hydrogen. That doesn't affect our experiment a whole lot right now, but you need to know that they are positively charged particles. So he's got this like laser beam that's got these alpha particles, and he shoots them into this gold foil, right? Real thin gold foil. And his expectation, based on the Thompson model of the atom, was that the particles would just pass right through the foil. Right? Because let's think about what we knew so far. At this point, we thought the atoms were spherical, that had negative charges and positive charges dispersed evenly throughout the atom. Right? That's what we thought so far. Agreed? And so yet we're shooting these little positively charged particles through this foil, and the expectation was that they'd come right out the back, right? Because nothing would be stopping them. Do we see how the thought process is going so far? Okay, and so that was the expectation, right? This is kind of what he thought it would look like. We would take the Thompson model, or what we knew about the atom at the time. The alpha particle here is the green one, and we thought it would just shoot right through. Okay, you don't have to draw this part out. I just wanted you to be able to visualize it. Okay, that was the expectation, was that those particles would go right through that foil, and he's got a little screen set up to know where those particles are coming out. Okay? However, that's what most of them did. Most of the alpha particles did pass right through the foil. But some of them were redirected at the source or at the foil. Maybe I want to put that. They were redirected at the foil. Okay? So they bounced off in a different direction. These little positively charged particles were redirected by something. So what do you think it could be that could cause a positively charged particle to redirect? Another positively charged particle, right? If you think about positives and negatives, they attract each other, right? But what do positives and positives do? They repel or they bounce off, right? So if I have a positively charged particle and it runs into another positively charged particle, it's not just going to go right through, it's going to repel, okay? Or it's going to bounce off. So his conclusion about that was that there has to be a small positive region at the center of the atom that's causing these alpha particles to redirect. Right? There has to be a positively charged region of the atom that is causing my alpha particles to redirect. Right? Otherwise, they would have gone right through, right? If they didn't hit something positive, there wouldn't have been any redirection. So his conclusion was that there's got to be some positively charged region at the center of the atom that causes a redirection of my particles. And he called that the nucleus. Okay? That's what he called the nucleus, was this small positively charged region. Okay, and then he said, well, if my atom has a small positive region, what are the electrons doing, right? His suggestion was that the electrons were orbiting this nucleus, similar to the way that planets orbit the sun. Okay, so he's got this model that looks, I'll show you his model here in just a little bit and I'll have you draw it out. But his suggestion was that electrons then orbited that nucleus. And if that is the case, if the electrons are orbiting the nucleus, that essentially means that most of the volume of the atom was empty space, right? Because you've got this little tiny nucleus that's highly concentrated with protons. And then you've got electrons that are orbiting around the outside. So depending on where those electrons are, that leaves a lot of empty space in the surrounding areas of the atom. Okay? So that's a really important part about his theory of the atom, was that it's a lot of empty space, right? Dense nucleus, electrons orbiting, and then empty space kind of in between there. And so his model was actually nicknamed the planetary model. Why do you think? It looked just like planets orbiting the sun, right? It looked like planets orbiting the sun. So I'll show you what it looks like here in just a minute. I want to show you a picture here of the gold foil experiment up a little closer. And then I'll show you the Rutherford model that I'll have you kind of draw out or sketch here. Okay, so here's a kind of an image or a clip art of what the gold foil experiment looks like, right? We shoot the alpha particles into the gold foil. This was what happened with the non-deflected particles. They hit the screen really pretty clearly right behind the foil. That would be an alpha particle that went through the empty space of the atom, right? Nothing was redirecting it. Then we had some that were redirected. And so what do you think happened to these three particles? What did they hit? They hit the nucleus of an atom, right? Of a gold atom. So they hit the nucleus of a single gold atom and were redirected. So that's essentially what happens there, right? His model now shows a more dense region of positive at the center of the atom. And then more realistically, here's what the Rutherford model looks like. This is a very typical like clip art chemistry atom model of the atom, right? This is what you see, I don't know, in pop culture about chemistry is what this looks like. Realistically, this is not really truly what we think the atom looks like today, but it does give us a good visual. So this is kind of what I do want you to go ahead and sketch out the Rutherford model because you'll need to be able to identify what that looks like. But I want you to think about this here. If there's an electron on that orbit, an electron on that orbit, and an electron on that orbit, and I take away these lines, there really truly is a lot of empty space in the atom, right? If I take away the lines on which it orbits, knowing it's going to follow those patterns, look how much empty space the atom is made up of, right? You'd have more than 3 electrons in bigger atoms, but there really is a lot of empty space. So that's kind of what that looks like. Go ahead and get a sketch of that so you have an idea.
Which one is that?
This is called the Rutherford model. Okay, or sometimes his is even called the planetary model because it looks similar to planets orbiting the sun. All right, so last thing we're going to talk about here is the nucleus, right? He called this positively charged region, the nucleus. But today we know that the nucleus contains two different parts, two different subatomic particles. What does it contain? Protons and neutrons. Okay, it contains protons and neutrons. So within the nucleus, protons have a positive charge and they have a mass of 1 AMU. Do you know what AMU stands for? Atomic mass unit. That's all it means. Atomic mass unit. It's the mass of an atom, right? A proton has a mass of 1 AMU. Protons have a positive charge. Like I said before, the proton or an AMU is about 2,000 times heavier than the mass of a single electron. Okay? Really, I think it's like 1,800 times heavier, but at that point, what's the difference? Okay, so protons have a positive charge and a mass of 1 AMU. Neutrons have a neutral charge or no charge and also have a mass of 1 AMU. So neutrons and protons weigh the same, right? They weigh the same, but neutrons have no charge. Protons have a positive charge. So in the nucleus itself, positives and neutrals would really not normally attract, right? Oh, sorry, Brandon, go ahead.
I have a question.
Uh-huh.
How do you know that's it?
All right, so protons and neutrons wouldn't normally be attracted. Positive and neutral wouldn't normally be attracted. So there's a special type of force within the nucleus that we call a nuclear force that holds those protons and neutrons together, right? Because normally negative and positive are attracted to each other, and positive and neutral wouldn't be, but they're called nuclear forces, and they allow that nucleus to stay together, right? It keeps those protons and those neutrons in place and in the center of the atom.